in the previous module, we are talking about the cyclopropenyl system. Application of HMO approximation to cyclopropenyl system. We obtained the 3 different energy levels. Out of these, 2 energy levels were degenerate. One was the bonding molecular orbital, and the rest 2 higher energy levels were degenerate state. For each of these, we obtained the wave functions also. So what was the wave function which we obtained? Psi1 was 1 over root 3, pz1 plus pz2 plus pz3. Then for psi, what we can do is that we can represent these functions like a like this representation. What we say is that we suppose this board to be a board of xy plane where your carbon is present, and then the lobe of the d orbital will be above the plane of the board and below the plane of the board. So if a person looks from the top, he will look at only one of the lobe which is on the top of the board. Okay, so one of the lobe of the top of at the top of the board which he will observe is given a dark circle if it is a positive lobe, and an empty circle if it is a negative lobe, a filled circle and an empty circle. So whenever you have a coefficients of positive coefficients, it will be a positive lobe, because if you know, if your coefficients, if your psi is equal to C1 psi1 plus C2 psi2. So two different, if you take C1 is equal to 1 and C2 is equal to plus minus 1, which we have seen, then psi becomes equal to psi MO becomes equal to psi1 plus psi2 and psi1 minus psi2. So a negative combination means if you have a positive lobe and a negative lobe, then this lobe will be a negative lobe and a positive lobe, because a negative combination is taking place. Okay, so a person which looks from the top will see one positive lobe here and one negative lobe here. In contrast to this, if it's psi1 plus psi2, he will look at both the positive lobe only if he is viewing from the top. So what happens here in psi1, you have all the coefficients 1 by root 3, which is a positive. So all these lobes C1, C2 and C3 positive lobe will be present, and the coefficients will be 1 by root 3, 1 by root 3 and 1 by 3. This is the way of representing the wave eigenfunctions of cyclic system which we obtain. Okay, and there is no change in the sign of the coefficients, all are 1 by root 3. So there is no nodal plane also. If you go for psi2 system, psi2 eigenfunctions which we obtained in the last module, it is 1 by root 2 psi pz1 minus psi pz3. Means if a person looks from the top, he will look at one of the lobe which is present on carbon number 1 will be a positive lobe, but another carbon number 3 lobe will be a negative lobe. So its representation will be like this one. C1 lobe will be filled lobe with a positive lobe, and C3 lobe will be unfilled because it's a negative lobe. Now, if the sign is changing, that we are looking from the light from the particle in a one-dimensional box, that if the wave function changes its sign, a node appears. So a node will appear here. This will be a node, and the nodal plane is shown as the dotted line. Okay, this is called base of the nodal plane in this particular molecule. If you go for psi3, then psi3 this is the wave function. Okay, and the coefficients here is the first coefficients at carbon number 1 is 1 by root 6, at carbon number 2 it is minus 2 by root 6, and carbon number 3 it is 1 by root 6. So it can be represented like this one. Now you see carbon number 1 positive lobe 1 by root 6, carbon number 2 negative lobe minus 2 by root 6 is the coefficients, carbon number 3 1 by root 6 and a positive lobe. Now you see when you go from C1 to C2, the sign of the wave function changes, so you will have a node here. If you go from C2 to C3, then also the wave function changes, so you will have a node here. So a plane which will cut both these points will be the nodal plane in the case of this psi3 cyclopropenyl wave functions. Okay, so this is one of the representation for which is very commonly used for cyclic system, which tells you the nodes also and which tells you the combination of atomic orbital also. that when it will be a positive lobe, when it will be a negative lobe. Okay. Once you, now the next task of doing of remaining task in the cyclopropenyl system is that you should be able to find out the electron density, charge density, and bound order of cyclopropenyl system. So again you have carbocation, you have carbon free radical, you have carbon ion. For all these systems we will calculate the electron density, charge density, and bond order. So the first system is cyclopropenyl carbocation. In case of cyclopropenyl carbocation, you have only 2 pi electrons, and which is present in the psi 1, that is the bonding molecular orbital. So what will be the charge density? Electron density. Electron density at C1 will be equal to 2 electrons are there, and it is present in psi 1, which is the bonding molecular orbital. So what is the coefficient here? 1 by root 3. So 2 into 1 by root 3 square. So it will be 2 divided by 3. Okay. Then at C2, what will happen? Again at C2 you have 1 by root 3 coefficients. Okay. And we are not concerned with psi 2 and psi 3, because psi 2 and psi 3 doesn't have electron. So electron density question doesn't arise there. Okay. At C2, again the electron density will be 2 by 3. And what does it mean? At C3, again if you look at this one, 2 into 1 by root 3, so coefficient is same everywhere, and you get the same electron density. If you calculate the charge density, cyclopropenyl carbocation you have, so Q1 and Q2 and Q3 are all same, 2 by 3. And if you calculate the charge density, at C1 the charge density will be 1 by 3, at C2 the charge density will be 1 by 3, and at C3 the charge density will be 1 by 3. So the total charge density will be 1 by 3 plus 1 by 3 plus 1 by 3 means equal to 1. And that is exactly expected for a cyclopropenyl carbocation. Because in a carbocation you have one positive charge. Okay. So total charge density, total electron density, total charge density will be equal to plus 1. Okay. Electron density was 2 by 3, 2 by 3, 2 by 3, and charge density is 1 by 3, 1 by 3, 1 by 3. So plus 1 charge is present in cyclopropenyl carbocation, and it is expected that the plus 1 charge will be there. Okay. Now if you look at the bond order, then again you are concerned with the psi 1 only, because electron is present in psi 1. So look at the coefficients of C1 and C2, and both are 1 by root 3. So 2 into 1 by root 3 square, and 2 by 3 is the bond order. If you go for C2 and C3, then again the coefficients is same. In the psi 1, the electron is present in the psi 1 only. So 2 into 1 by root 3 square is equal to 2 by 3. Then again for C1 and C3, so it is the same coefficients, 1 by root 3. So this also gives you the bond order. 2 by 3, 2 by 3, 2 by 3 is the bond order in each case, in case of cyclopropenyl carbocation. What happens to carbon ion? If you look at the carbon ion, there are, this is carbon free radical, I think. Okay, this is carbon free radical. No. Carbon ion, 2 electrons in psi 1 and 2 pi electrons, 1 pi electron each in psi 2 and psi 3. Okay, fine. You have 4 electrons here. It's good. Fine, it's fine. 4 pi electron are present. So you have 2 pi electrons present in the bonding molecular orbital psi 1, and 1 electron in both the psi 2 and psi 3. Okay. So if you have to calculate the electron density at C1, you will have to calculate 2 electrons for C1 is 1 by root 3, then 1 electron for 1 by root 2, and 1 electron for 1 by root 6. Actually the wave functions should be with you when you are calculating this one. So what you can do is that when you see for C1 you have 1 by root 3, 1 by root 2, and 1 by root 6. Okay. So for carbon ion, 1 by root 2 and 1 by root 6, so total charge is 4 by 3. Okay. At C2 what happens? Again 2 into this psi 1 is same, psi 2 does not have C2 coefficients. So C2 coefficient is 0. Psi 2 doesn't have C2 coefficient, so it is 0. Psi 3 have C2 coefficients as minus 2 by root 6. So this also comes out to be 4 by 3. Then psi 3 comes out to be 2 into 1 by root 3. plus 1 into minus 1 by root 2. It was plus 1 by root 2 and here it will be minus 1 by root 2, and then it is plus 1 into 1 by root 6. So this also comes out to be 4 by 3. And if you sum these two, all these, if you calculate the charge density at C1, what will be this? 1 plus 1 minus 4 by 3, so it is 1 by minus 1 by 3. Again 1 minus 4 by 3, so minus 1 by 3. Again at C3, it is minus 1 by 3. And so total charge density will be minus 1, which is expected for a carbon ion. You have a carbon ion, so the charge should be minus 1 and the charge is minus 1. Okay. So the Huckel molecular orbital treatment of the cyclopropenyl system gives you a plus 1 charge for cyclopropenyl carbonium ion and gives you a minus 1 charge for cyclopropenyl carbon ion. It means whatever calculation you are doing is the right calculation. Okay. If you calculate the bond order calculation, then the bond order comes out to be 1 by 3. Again, it's the same thing which I am repeating time and again. For C1, the coefficient is, for Psi1, the coefficient is root 3, 1 by root 3 and 1 by root 3. So this you can write. These are the coefficients from Psi1, okay, for C1 and C2. These are the coefficients from Psi2 for C1 and C2. C2 coefficient is 0. And these are the coefficients from Psi3. So it is 1 by root 6 and minus 2 by root 6, and one electron is there, 1 electron is there, or 2 electron is there. Okay. So these are encircled number or number of electrons. This is, student get confused with this number. How do we multiply? So number of electron multiplied by the coefficients of C1, coefficients of C2 in Psi1. Then number of electron multiplied by coefficients of C1, coefficients of C2 in Psi2. Then number of electron multiplied by coefficients of C1, coefficients of C2. If you don't have the electron, neglect it, because multiplication by 0 will omit the term. Okay. So here you have 2 by 3 minus 2 by 6. It comes out to, bond order comes out to be 1 by 3. Same way you can calculate for C2, C3, and this comes out to be 1 by 3. And if you calculate for C3, C1, then also it comes out to be 1 by 3. So everywhere it is the same thing. You see the calculation is, these are the coefficients from Psi1, these are the coefficients from, for 2, 3, again for 2 it is 0, for 2 it was 0, Psi2, and for this one, this multiplied by roots, this and this one, it is Psi3, 2 and 3. Okay, same thing. So bond order also we calculated for carbon ion. So we calculated electron density, charge density, and bond order. If you have carbon free radical, cyclopropenyl carbon free radical, then also we can calculate the system. Now here you have 3 electrons. So 1 pi electron is either in Psi2 or in Psi3, because both are degenerate state. Okay. So in any one of this we can take Psi2 and Psi3. Since 1 pi electron in Psi2 or Psi3 degenerate set, we assume half electron to be present in each degenerate orbital for electron density calculation. Now here also it's a departure. You see, in cyclopropenyl system, something new you are learning. The first time you came across while applying HMO that you are getting a degenerate state. If you are getting a degenerate state, then how to find out the coefficients that we observed? That one of the coefficients you guess, and for the next coefficients you apply the orthogonality condition. Here again we are calculating the electron density, and now for electron density calculation I say that one electron is present in either in Psi2 or in Psi3, but both are degenerate. So for electron density calculation you suppose that half of this is present in Psi2 and half of this is present in Psi3, and if you suppose this, then your calculation gives electron density Q1 at 2 into 1 by root 3 plus 1 by 2 is the number of electron. Now you see there is nothing like 1 by 2 electron, but it is theoretical calculation which will give you a good number. This supposition that since it's a degenerate state, so electron can go to Psi2 and Psi3 both. So we can suppose half of this to be present in Psi2 and half of this to be presented. So this is actually number of electrons. Half electron doesn't mean anything, but just a theoretical calculation which gives you a good number. So electron density C1 comes out to be 1. Then again, if you calculate electron density at C2, this also comes out to be 1. If you calculate electron density at C3, this also comes out to be 1. And what does it mean? It means that charge density at all C1, C2, C3 will be equal to 0. Okay? Because all electron density is 1 and it's expected. It's carbon free radical. Now, it's neither carbocation nor carbon ion. We have seen that for carbocation, you got plus 1 charge. For carbon ion, you got for minus 1 charge. But it is cyclopropenyl carbon free radical, so that there should not be any charge present. And it's the fact that the charge density which you calculate comes out to be 0. Okay. Now, if you calculate the bond order of carbon free radicals, then you see the bond order comes out to be 0.5 between C1 and C2. Okay. And again here also for bond order calculation also, the number of the electron in the two orbitals remains 1 by 2 and 1 by 2, Psi2 and Psi3. Okay. So with the carbon free radical, what you got, that if you have a degenerate state where only one electron is present, two degenerate state, then you take half electron in one state and half electron in another state. Okay, for the calculation. And in C2 C3 bond order is also 0.5 and C3 C1 bond order is also 0.5. Okay, so this gives you a complete analysis of cyclopropenyl carbocation, cyclopropenyl carbon free radical and cyclopropenyl carbon ion. Okay, so the first thing is writing the secular determinant, getting the value of x for, and then getting, once you have the x value, you have the energy levels. Once you have the energy level, then you can put the electrons according to the quantum energy state. Then the next task in HMO approximation method is that you find the coefficients value. Here we have found the value of A1, A2 and A3. For that, again you write the matrices and you write simultaneous equation. Okay, and then you find out the value of A1, A2 and A3. And if you find the value for a particular x value, okay, if here x was -2, we have started with -2 and +1 +1. So x we have started with -2 and we got the value of all the coefficients A1 and A2 and A3 equal to 1 by √3. Then I said you that for finding out the coefficients of Psi2 and Psi3, they are degenerate state. So for the degenerate state, what you say that arbitrarily you can put any one of the value, because all the simultaneous equation you get is same. A1 plus A2 plus A3 is equal to 0. Here we were getting, because x was +1. So all three equations is A1 plus A2 plus A3, A1 plus A2 plus A3, A1 plus A2 plus A3, and you have three unknowns. So you cannot get it, you cannot calculate it. So what we say, the way out is to suppose, to assume one of the functions, one of the coefficients to be arbitrarily equal to 0. And then we proceeded from there and we calculated the value of A1, A2 and A3 for Psi2 and Psi3 values. Okay, using the next value we obtained using the orthogonality condition. After getting the wave functions, we calculated the electron density, charge density and bond order for all cyclopropenyl carbocation first, then carbon ion and then carbon free radical. And here also the new lesson was that if you have a degenerate state, then half of the electron will be counted for calculation of electron density and bond order. Okay. Now the next system which we are going to start with, we will not be able to complete it, but I will start here, will be a butadiene system. Now again, I did allyl system which was a linear molecule, and then we came for a cyclic system, cyclopropenyl. So we will start with butadiene system, a linear system, 1,3-butadiene, and then again we will, after this what we will be doing is cyclobutadiene. Okay. So in a butadiene system you have 4 carbon atoms, C1, C2, C3, and on each of these carbon atoms you have, it's 1,3-cyclobutadiene that you are aware of. What is that? CH2, double bond CH, single bond CH, double bond CH2. So you have on each of these CH2, CH, CH, CH2, on each of these you have a pi p orbital which overlaps. Okay. So we have 4 pi electrons or 4 p orbital system here in case of this one. Okay. And so a 4 by 4 determinant you will obtain. Your wave function here will be psi mo will be a1 phi 1 plus a2 phi 2 plus a3 phi 3 plus a4 and phi 4. And when you do linear variation treatment, then what does it mean? Just for refreshing your memory, you find out the energy with the Rayleigh ratio and then you differentiate energy with respect to a particular coefficient. So what you will do here, you will do del E by del A1, keeping rest of the thing is constant, A2, A3 and A4 constant. Then you will do del E by del A2, keeping A1, A3 and A4 constant, okay, and so on. So from each of these differentiation, you will get four simultaneous equations, and the 4 simultaneous equation will give you this circular determinant that we have done already. So there is not, just to refresh your memory, I have written it. Okay, but this is your wave function. Okay. Now since we have this determinant, so we can write in terms of alpha and beta this determinant. So you write in terms of alpha and beta, and you see here you have C1 and C2 is connected directly, so it's alpha minus E, and alpha minus E will be there, but H12 beta 1,2 is connected directly, so it's beta. 1,3 is not connected, so it will not be beta, it will be 0, and 1,4 is also not connected directly, means there is no sigma bond between carbon number 1 and carbon number 4, so it is 0 also. Then H21 again connected directly, so it's beta, and all diagonal terms has to be alpha minus E, that you have seen, and why it is so I talked about many times. Okay, so diagonal terms alpha minus E. Then again you have in the this one is 2,3. 2,3 is connected, so it's beta, but 2,4 is not connected, so it is 0. Then again 3,1 not connected, 3,1 not connected, so 0. 3,2 is connected, so beta. Then diagonal term alpha minus E. Then you have 3,4. 3,4 is connected, so it is beta. Then 1,4 not connected, 0. 4,1 and then 4,2. 4,2 is also not connected, so 0. 4,3 connected, so beta. And this is the diagonal term alpha minus E. Okay, so this again check the diagonal terms. I am saying you all diagonal terms is alpha minus E. So we have written the circular determinant, and in terms of x, if you want to write, it will be all alpha minus C will become x, and all beta will be equal to 1, and rest of the term will be 0. So x1 0 0, 1 x 1 0, 0 1 x 1, 0 0 1 x. Now you have to solve this determinant. See, gradually when the number of electrons are increasing, what is happening? The determinant size is increasing, and so finding out the value of the determinant will become more and more difficult. Okay, if you go for a 10 pi bond system or 12 pi bond system, it will be very difficult to solve this determinant. But there are ways to find out. Certainly we will not do that, because it is based on the symmetry, and symmetry we are not going to do in this lecture. So those of you, if you have done an additional course on molecular symmetry, then you can go and look into the book that for larger system where you have more number of pi electrons, how to solve this determinant and get the value of x. That can be done through using the symmetry. Okay. So this is the determinant, and if you have to solve this one, I have done it stepwise, because one of you may not have done much of the mathematics. So it's a stepwise solution for you. Now what you can do is, now if you take this x here, the determinant which remains is this one, is this determinant. So this determinant is copied here. Okay. Then you take this value 1 here, and the determinant which remains is, not excluding this line 1 0 0, 1 0 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 0, 1 0 1 this line 1x, this column 1x1 and then 0 1x. Rest of the part, it should have been 0 multiplied by other determinant also and again 0 multiplied by another determinant also. But since we are multiplying by 0, so this will go. Okay. So you have this value. And finally, what you get is x raised to the power 4 minus 3x square plus 1 is equal to 0. So you have to factorize this value, and if you factorize this one, you can write this in the form of y, if y square minus 3y plus 1 is equal to 0. And so the value comes out to be y is equal to 3 plus and minus root under b square minus 4ac divided by 2a, that you know. It's a quadratic equation. So the value comes out to be 2.618 and y is equal to x square. Here it comes out to be 0.382 and again it is equal to x square. So what is the value of x? X is equal to plus minus 1.618 and here also x is equal to plus minus 0.618. If this is the value, then we can write the eigenvalue or energy value. So the first energy value, if you write x is equal to minus 1.618, then energy comes out to be alpha plus 1.618 beta for bonding molecular orbital. Okay. Then if you write x is equal to minus 0.618, then E2 comes out to be alpha plus 0.618 beta for bonding molecular orbital. Okay. If you have x is equal to plus 0.618, then you get E3 and that is alpha minus 0.618 beta for anti-bonding molecular orbital. If x is equal to plus 1.618, then E4 comes out to be alpha minus 1.618 beta for anti-bonding molecular orbital. Okay. Once you have this one, then you look at this problem. In the allyl system also, what the energy value which you got were the three different energy value: bonding, non-bonding and anti-bonding molecular orbital. In case of butadiene system also, what you are getting is 4 different values: alpha plus and naturally, remember alpha and beta are both negative quantity. So this will be the lowest energy level and it will be bonding molecular orbital. Then it is 0.618 again, but plus, so this will be the next energy level and so this will also be a bonding molecular orbital. Then again for E3 you have alpha minus 0.618. So beta is also negative, so negative and negative will make it positive, but alpha will remain negative, so it will be less negative and it will be an anti-bonding molecular orbital. It will be higher value in the energy, and same will be the anti-bonding molecular orbital. Okay. Once you have this one, then you can write the different energy state. So alpha plus 1.618, alpha plus 0.618, alpha minus 0.618, alpha 1.618. So we say this to be bonding molecular orbital, this to be bonding molecular orbital, and these two are anti-bonding molecular orbital. Okay. So this is bonding molecular orbital. This is also bonding molecular orbital. This we say anti-bonding molecular orbital. This we say anti-bonding molecular orbital. And how many electrons we have? Here we do not have a choice. We do not have a carbocation and carbanion and cyclopropenyl system as we have in those systems. So here we have 4 electrons in a in a butadiene molecule. So 2 is present here and 2 is present here. So what will be the E pi? 2 electrons is present, so 2, and what will be the energy? Alpha plus 1.618 beta. Then 2 plus 2 electron, alpha plus 0.618 beta. So the total energy which will come out to be will be E pi will be 2 alpha 4 alpha plus 4.472 beta for this particular system, butadiene system. Now if you have an ethylenic bond, 2 ethylenic bond, then what will be the energy? Energy of 2 ethylene bonds will be 2 into 2 alpha plus 2 beta. So it will be 4 alpha plus 4 beta. 4 alpha plus 4 beta. And if you subtract this from this one, what you have, then it will give you an energy value. This value is for butadiene, and this value 4 alpha plus 4 beta is the value of 2 ethylenes. So if you subtract, you get the delocalization energy equal to 0.472 beta. So 2 separate ethylene molecules, and if you have a butadiene molecule, then butadiene molecule is more stable as compared to 2 separate ethylene molecules. That says the delocalization leads to decrease in the value of energy and stability is gained whenever the electron is delocalized. Okay, so this is what is the eigenvalue which we did. Okay, after doing the eigenvalue, the next task which we have to do is finding out the eigenfunction for the beta diene system. Okay, and once we find the eigenfunction of the beta diene system, then again we will be doing calculation of electron density, charge density, and bond order. So this will be we will be doing in the next module. Okay, thank you.